So this section is on atoms and light. We're going to be talking about how atoms play a role in how light is produced. Oops. This is the picture of the Bohr model of the atom. And in Bohr's model, we talked about this just a little bit about how all the mass is at the center of an atom. That's where the nucleons exist. Those are the neutrons and the protons. And then the electrons orbit around that. According to Bohr, they call it the planetary model, where the electrons are in circular orbit. It's actually a lot more complicated than that, but it's not a bad way to think about it. And so electrons are in these well-defined orbits in atoms, and they're different for different atoms. So let me see if I can do this. There we go. And so, you know, if this is here's an atom, and it's got an orbit here, and it's got an orbit here, and it's got an orbit here. And you can kind of think of these as seats in an amphitheater. You've seen those old stages, those old theaters maybe where there's a stage in the middle somewhere, and everybody can sit all the way around the stage. Well, in the middle is our nucleus, and the rows of seats are the electron orbitals. Let me see if that's gonna come back into focus at some point here. There we go. And so an electron can be living here, or it can be living here, or it can be living here, or it can be living in the outer one here somewhere. But it doesn't exist in between. It either hops to this one or hops to this one. It's like people in rows of seats. You don't have people between the rows. In principle, you could, and with electrons, you can't. But the idea is that they're always in a set of orbitals, and each element has different arrangements of rows of seats. They're all centered around the nucleus, but they might be spaced differently. A different atom might have, you know, its rows might be packed in a little tighter or something like this, and then maybe they'll have a bigger gap and a bigger gap out here or something like that. And each atom is different. Each element is different. All the hydrogen atoms are the same, all the helium atoms are the same, but they're different from each other. So getting back to our original picture here, we number from inward outward, and so these are sometimes called orbitals or energy levels. And so this is n equals 1, this is n equals 2, this is n equals 3. That's how we count the orbitals. That's the row you live in. That's the energy level you're on. So you can be electron in energy level 1, or electron in energy level 2, electron in energy level 3. Notice it says it increases as you go outward. So if an electron is in energy level 1, it needs to gain energy to go to a higher level. Or it can lose energy and go to a lower level. What's interesting is that it has to, if it's going to go to the n equals 2 level, it has to gain exactly the energy difference between these two to go. It can't gain a little more because that won't put it in that energy level. And so it has to find a way to get exactly that amount of energy. So let's just read these. Electrons orbit the nucleus in orbits that carry well-defined energies. Everybody's in the n equals 1 energy level has that energy. Everyone is n equals 2 has that energy. The available orbits for electrons are restricted. Electrons cannot just be in any orbital. They can't be anywhere. They have to be in those specific orbits, right? The ones we've drawn or listed. In order to move to another orbital, in other words, in order to go to a new energy level, the electron has to gain an energy or release a certain amount of energy. And so electrons can gain energy to go to a higher level by either absorbing a photon or being bumped by another electron. So let's go to my drawing again. I'll try to do a better drawing here. Right. So here's an electron here. Here's an orbital here. I'll just draw two orbits, right? And this is my n equals 1, and this is my n equals 2. And so I've got an electron in here. It's just sitting here, right? And so it's not sitting. They're moving all the time. But So if it wants to go to this one, or if it gets, if it's going to this one, if it's going to the n equals 2 level, it either has to absorb a photon. We usually draw that this way, so we'll have a little arrow, and I'll draw a little photon away. And the energy of this photon has to be exactly the difference between these two guys for this guy, otherwise it won't absorb it. And so if it's just the right amount of energy and it can jump to there, it'll absorb that photon and pop up to the next one, or it can be bumped by a passing electron. And as long as it takes exactly that amount of energy from the electron, it can also pop up to there. And so electrons can gain energy. Electrons can gain energy by absorbing a photon or being bumped by another electron or something else, but it's usually just being bumped by an electron. Electrons can release energy. In other words, now we can say, look, now the electron's up here, right, and it's going to go down to here. So now it can release energy. It can spit out a photon, lose that energy, and drop to the lower level, or it can bump another electron. I'll just have a little electron here that's passing by. Maybe I won't draw it on the atom somehow. It's a free electron somehow, and it just happens to be passing through, and it can get bumped and lose some energy to this guy, and then it pops down to the lower level. And so they can either jump up to a higher level by absorbing a photon or bumping an electron, or drop to a lower level by emitting a photon or bumping an electron. Any electron can only gain or release an amount of energy that exactly corresponds to the energy required to go to another orbital. That is to say, any electron that's in the atom, if it's in this orbital, if it's going to go to this one, it has to gain exactly that amount of energy. It can't gain a little extra and just keep it. It either has to have exactly that amount of energy or it won't make the jump. So all this is to say that when you have electrons in atoms, they have very specific energies, and their energies can only change by very specific amounts. By the way, they're not restricted to just jump to the next one. If I draw another orbital out here, hang on a second, let me draw this again. If I draw an n equals 3, an electron can also jump from this one to this one, skipping the second one, as long as it gains exactly the difference between these two in energy. And so here's another picture of it, right? And so here's when an electron in an atom absorbs energy from a photon, the electron can jump to a higher energy level. The greater the photon energy, the farther the electron can jump, but the photon has to carry exactly the amount of energy between the two levels. An electron can emit a photon and lose energy to drop to a lower level. And so you can see that here's an electron that's going from the n equals 1 to n equals 3 level. So this guy here is going from the n equals 1 to the n equals 3 level, and notice he's absorbing a photon that's got a short wavelength, right? Short wavelength photons are higher energy. So it's a higher energy photon. This guy is going from the n equals 2 to n equals 3. That's a smaller amount of energy, and so it's absorbing a longer wavelength photon, a lower energy photon to do that. This guy's doing the reverse of those things, and so instead of absorbing photons, he's releasing them, but there you go. So explain how electrons and atoms interact with light. And so an electron can absorb a photon if the energy in the photon corresponds to the difference between the electron's current energy level and any higher energy level. An electron can also be bumped by another electron, and if the energy is just right, it'll absorb that energy and jump to a higher level. In this section, this is sort of a summary of what we've been talking about. An electron can emit a photon of light if the energy of the photon corresponds to the energy difference between the electron's current level and a lower energy level. And so when these electrons are jumping between levels, they're spitting out photons whose energy corresponds to the energy level differences in that atom. And that's why we see very discrete spectra. In the last section, we were talking about, at the end, we were talking about atomic spectra, right? And there's specific lines. We call them atomic spectra, or emission spectra, or line spectra. And the reason they're very discrete sets of lines is for this reason exactly. The exiting photons, the emitted photons, can only have energies that exactly correspond to the energy spacing of the electron orbitals in atoms. This was a big discovery that happened at the beginning of the 1900s and really explained an open puzzle that had been around since the middle of the 1800s, before they really understood what atoms were. This was happening during the beginning of our understanding of how atoms work. So this is a little more specific schematic of the energy levels of the hydrogen atom and the transitions the electrons can make to and from these different levels. And they're labeled according to what series they are. And so this is the, anything into or out of the n equals 1 level is called the Lyman series. And you can see this is the n equals 2 to 1 level, there's a 3 to 1 level, there's a 4 to 1 level, there's a 5 to 1 level, and there's a 6 to 1 level. But it goes on and on. There's an infinite number of energy levels. Actually, as you get out farther and farther, they get closer and closer together, so the diagram isn't perfect, but it's not bad. You'll notice that the wavelengths are decreasing for the higher energy drops. A shorter wavelength photon is a higher energy photon, so an X-ray has a shorter wavelength than a visible light photon, and an infrared has a longer wavelength than a visible light photon. And so it turns out that the Lyman series, this is only for a hydrogen atom, by the way. A helium atom or any other atom would have a completely different set here of these wavelengths. These wavelengths, again, correspond to the wavelength of a photon that would be emitted or absorbed for a transition from n equals 1 to whichever one of these levels we're talking about. For beginning or ending at the n equals 2 level, those are called the Balmer series, and you can see these are longer in wavelength than all of these guys. It turns out the Lyman series is in the ultraviolet spectrum, and so when hydrogen emits in the Lyman series, that's not visible to us. This is the set that's visible to us, and so in visible light astronomy, or in other things, this is what we see. When we see a spectrum for hydrogen with our eyes, this is what we see. We can detect all these others with ultraviolet sensors, but not with our eyes. Similarly, for the n equals 3, the Paschen series, you can see that all of these guys are longer wavelengths than all the rest of them. This is a lower energy. These are lower energy photons. All of these guys are in the infrared. The ones going into the n equals 4 level are called the bracket series, and those guys are a lower energy still, but still in the infrared, because the infrared is such a wide energy range, wavelength range. So you can take this chart here and you can sort of redraw it in a more sort of rectangular way, and it looks like this, where down here is the n equals 1 level, this is the n equals 2 level, this is the n equals 3 level, and so on. And you can sort of see that this gives a better depiction of the infinity of levels, sort of. And now you can see that these levels are clearly not evenly spaced. Right here we're talking about the energy, and these negative energies just indicate that the electron is trapped. So when you're in the n equals 1 level, it's the lowest energy level for an electron, and if it wants to get out of that atom, it's got to gain all that energy back. And so an electron that's trapped at the lowest level needs 13.6. These energy units are electron volts to escape to the n equals infinity level, which kind of makes it free. If it gets more energy than that, it can be gone. It can also get out, but it has to get at least that much energy to completely escape. If it doesn't have enough energy to escape, it has to get like 13.6 minus negative 3.4. What is that? Is that 10.2? So the difference in energy between the n equals 1 and the n equals 2 is 10.2 electron volts. And so it would take a photon carrying that much energy to hit an electron at this level and get it up to the n equals 2 level. Less than that for this guy, 2 to 3 and 3 to 4 and so on. Notice if you look at the Balmer series, which is the visible light series, it's got colored lines. This n equals 2 to n equals 3 is a very common well-known line. I think it's 656 nanometers. It had it on our previous slide. Let's just go look really fast. Yeah, 656 nanometers. You can kind of see it right there. That's a very well-known hydrogen line. And when you look at a picture of a galaxy, which we will later on in the semester, you'll see it's got they have pinkish colors to them. That's that N equals 2 to N equals 3 hydrogen line. This is the other hydrogen line. It's green, and there's a blue, and there's a violet. There's a couple of violet ones, and you might see these are just much less likely. And so the ones we see most often are these several here. And if you break down the light, again, you get these spectrum by running light through white light through a prism, like you might have done with your kids, and seeing that rainbow. And so you would see the line spectrum of this by doing that. So here's some questions. What's responsible for the atomic spectrum emitted by hot gases? And so those would be the energy levels and a discussion of the energy levels. Why are there individual lines and not continuous spectrum? We talked about this, right? It's that these energy levels are discrete. This is, by the way, why it's called quantum mechanics. They're specific quantities, and they're not, you can't just have any value in here. You can't emit a photon of just any level. An electron can't jump to just any amount of energy. It's discrete. And so they say it's quantized, it's broken into specific quantities. And that's why you hear the word quantum mechanics. This is kind of a crazy idea. It took them a long time to figure this out. It would, it's sort of like saying your car can't have any speed. It can only go 10 miles an hour or 20 miles an hour or 30 miles an hour, but it can't go 26 miles an hour. This is a crazy idea to these people, but it's the correct explanation. All our science is based on it, and it works perfectly, or at least extremely well. So what are two ways an electron can gain energy? In other words, go to a higher level, right? We talked about that, absorbing a photon or getting bumped by an electron and so on. If an electron jumps from the N equals 3 to N equals 2 or N equals 3 to N equals 1, how will their wavelengths compare for the photons emitted, right? So N equals 3 to N equals 2, does that have more energy or less energy than N equals 3 to N equals 1? And what does that do to the wavelength of the photon, or the energy of the photon that's being spit out for those two transitions? You could look those up in the tables earlier and compare them, right? Which series in hydrogen is the visible spectrum? If a hydrogen atom emits a photon that's in a visible spectrum, what energy level did it fall into? Right? So you should be able to answer those. So the last part of this section, we're going to talk a little bit about the Doppler effect. You're familiar with the Doppler effect, and I'm just going to go through it for sound first because I think we're all a little more familiar with that one. And so here's the idea. If a car is playing a siren, this could be a police car, an ambulance, or something like that. In this case, they've drawn a sports car, but that's fine. If it's just stationary and you're listening to it, then everybody hears the same tone. These circles on here are supposed to be like individual waves. So I don't know how to draw it. We'll see some pictures in a second, but you can think of these things as like oscillating waves, right, that are oscillating this way, but in all directions, like ripples in a pond. And these are the peaks of the wave, right? The circle lines are the peaks, right? But in between, there's a trough, and it goes down and back up to a peak, and then down and back up to a peak, right? And so the wave peaks are hitting both people at the same time. Now what we're going to do is we're going to say, well, let's let the car be going in one direction instead of staying still. And so if you'll notice, the car is still playing a siren, but it's moving while it's doing that. And so as it's emitting these wave peaks in the forward direction, it's chasing after those wave peaks while it's going, and so the wave peaks are bunched up in the forward direction, and they're stretched out in the backward direction. Now, I would argue you've had this experience. If an ambulance is approaching you, you hear a high pitch compared to when it's receding from you, where you hear a low pitch. So it goes, right, as it goes by. What you're hearing is the crunched waves together So you hear a higher frequency because more wave peaks are going by you per second, right? And that's how we determine the frequency. Somebody behind, the waves are getting stretched out, and so they hear a low frequency. So after the car passes, you're in the behind area, and you get a lower pitch. By the way, so you get the same effect if the car is stationary and you're moving. This person on the right is running through the sound waves, so she's getting to them faster, right? If she was just standing there, they would come to her at a certain rate, but instead she's running towards them, and so she gets them more quickly. This person on the left is running away, and so they're getting to this person less frequently, and so the person on the right hears a high frequency because she's approaching, and the person hears on the left hears a low frequency, excuse me, because they're receding. So this is the Doppler effect with sound. Sound is affected by the pitch you hear is affected by both the motion of the source and the motion of the observer. And we have a lot of experience with this. By the way, this very thing is used in lots of medical applications to watch blood moving through coronary arteries and things like that, looking for various things inside your body and examining a fetus during a sonogram. Sound is used in a variety of ways, but also the Doppler effect is used to determine motion of stuff inside. So it's a pretty well understood technique. It's very well understood. It turns out for the Doppler effect, you just need waves. It doesn't have to be a sound wave or a light wave. It can be any wave, but we use it for light mostly in astronomy. We also use it for a sound in geology. So here's the Doppler effect with light, which is what we really want to talk about, at least at this point. It's developed by Christian Doppler in Austria. In 1842, he's studying binary stars, and he noticed that the spectra of these stars was shifting. And I'm going to talk about that a little bit as we go. But it turns out in a binary star system, if they're sort of spinning the right way, one of them will be approaching you while the other one's receding. About half of the stars in the sky are binaries, that is to say, two stars orbiting each other. That could have happened in our solar system. If Jupiter was about 80 times bigger, it would be a star. I mean, it's a lot, but it was at least possible. And so, since they're orbiting around each other, sometimes they're approaching and sometimes they're receding from you if you're looking at them edge on. That's what Doppler is doing. And so the Doppler effect is the shortening of the wavelength of a wave emitted in the direction an object is moving, and the lengthening the direction opposite. Just like with the car, the waves are shortened in the forward direction and stretched in the backward direction. It can happen with any type of wave, but we'll talk about light waves at this point. So let's just talk about a yellow light source, right? Because it's the easiest one to talk about. The yellow light is in the middle of the range of wavelengths, right? Red is the long wave, and blue is the short wave for the visible spectrum, or violet, if you want to say violet, is fine. We usually just say blue. So if an object is emitting yellow light, this is now like our car, right? And it's emitting yellow light. Well, if it's racing towards you, those wavelengths are compressed, and if it's going fast enough, they'll appear blue to you in the same way that, a car that's emitting a siren that's playing the note F might give you a high C if it's going fast enough, right? And so when something's moving towards you, from an optic standpoint, from a light standpoint, we say it's blue shifted. The wavelengths of the light are shortened, and so since the shortest wavelengths of light are at the blue end of the visible spectrum, we call it blue shifted. Similarly, if the yellow source is moving away, we say it's red shifted. And really, regardless if it's visible or not, we'll say the light is red shifted for something that's moving away, or it's blue shifted for something that's moving towards you, even if it's like in the X-ray range or something. Objects that are moving towards you, their light is blue shifted. Objects that are moving away, their light is red shifted. Here's a schematic of that, right? When the yellow light is receding, the observer sees a longer wavelength because the waves are stretched out. When when the yellow light is approaching, the observer sees a shorter wavelength because the waves are bunched together. It's not the best schematic, but it makes it reasonably clear. So suppose that a star appears blue. Here's the question. You see a star in the sky and it's blue. How do you know how do you know if it's a relatively stationary star? In other words, it's like the car that's not moving and it's just emitting blue light because it's blue, or if it's a yellow star that's blue shifted because it's approaching you, or if it's a red star that's just approaching you even faster. That's a tricky question. When the star appears blue, how do you know why it's blue? Right? And so the answer comes in these atomic spectra that we've been talking about. It turns out we can break down the light from a star and see its spectrum, see these little lines. Usually it's an absorption spectrum. I won't go into why, but often it is. And so we can see its hydrogen lines by breaking that light down, or we can see its helium lines and so on that we saw in the last section, those dark lines across a continuous spectrum. If the star is stationary, the lines in the spectrum will appear in all the usual places. But if the star is moving, those lines will be shifted. And that's how we know if it's just a stationary blue star or if it's a star that's approaching us or receding from us. And so here's a, oops. Try again. I got that right. Let me try one more time. Here we go. If you look at this diagram, the middle picture is the spectrum taken of the star, or this example, when the star is at rest. A star usually gives you a continuous spectrum, and the gases around it are the ones that put this absorption spectrum on top of it. But that's fine because they're moving with the star. And so this might be, this looks like a sodium spectrum, but it doesn't matter what it is. A star emitting sodium, say, would look like this when it's at rest. And then when it's moving towards you, every line in the sodium spectrum is blue shifted a little bit. And so we can tell by just seeing the same set of lines shifted a little bit and say, aha, that's the sodium line that's been shifted because the object is moving towards me. And there's no other element that gives that same fingerprint. And so we know that that's sodium or hydrogen or whatever it is. Every one of those, every one of the spectra, computers really, but we can pull out what the elements are. And there's usually 50 of them or something, or more, because some of them are ions. So there's many of them. Similarly, if it's red shifted, it's got all the same set of lines, but they're shifted towards the red. And so it's pretty easy for us to tell if the object is stationary or whether it's moving. And then by looking at the amount of shift, it tells us its relative speed, how fast it's going relative to us. It really just talks about its forward or away direction. We call it the relative velocity. And so what we do when we look at distant objects is we pull out a spectrum from them. And first of all, it tells us what gases are around them, right? By just looking at which sets of lines are in there. And then second, we can look at the shift in the lines and tell how fast it's going. It, by the way, doesn't tell us how far away it is. It just tells us the relative speed. How far away is a different set of tricks, which we'll talk about later on. So a little bit about that. It turns out the universe is expanding, and you might ask how we know that. People ask that a lot. The universe, it turns out, contains billions of galaxies. We lived in one we have named the Milky Way. But there are billions of them in the universe, and each contains billions of stars. Our galaxy, the Milky Way, contains about 100 billion stars. Other galaxies are similar. Some are smaller, some are bigger. It turns out that when we look at distant galaxies, they are all redshifted. That's kind of surprising if you thought the universe was sort of stagnant or something. But all distant galaxies are redshifted, and not only that, the farther away they are, the greater the redshift. That means the farther away they are, the faster they're going. Well, if there was a giant explosion and you waited a while and nothing was getting slowed down because of the vacuum of space, the farthest away objects would be the ones that were going the fastest. And so that's why astronomers are constantly talking about the expanding universe. This is the fingerprint of the expanding universe, the fact that all of the galaxies we look at are redshifted, and their redshift increases the farther away they are. It's the origin of the notion of the Big Bang. If you get interested in that, there are lots of popular books that have been written about the Big Bang. There's a lot of irony about it, because all of the great scientists of the day when it was first proposed hated the idea, including Einstein. The term Big Bang was coined by a British astronomer named Fred Hoyle, who thought the idea was preposterous, and he just gave it the silliest name he could give it. And sometimes those stick, especially in the sciences. So the Doppler effect is a very useful tool for us to explore our own galaxy and the only things, the things in our own stellar neighborhood, to tell which ones are approaching us and which ones are receding from us. And we can also use these spectra to tell what things are composed of, even though they're billions of trillions of miles away, or thousands or millions of light years away. And so these are all very useful tools, especially in astronomy. So there are here a few questions. What is the Doppler effect? Give an example with sound. If you could look at the hydrogen spectrum of a star, how could you tell if it was approaching? How could you tell if it was receding? Suppose you had the hydrogen spectrum from two stars, both of which are approaching. How could you tell which one was going faster? Right? Suppose you see a blue star in the telescope, how could you tell if it was blue due to the Doppler effect? Right? So these are some other questions.